Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. So today we're going to talk about Venus and the existence of life in the atmosphere of Venus. And for this, I invited two researchers who have been working recently on the two scientific papers and on the recent controversy whether or not we have life in this upper atmosphere. So let me first introduce to you Alex Akins. Hi, Alex. How are you? Alex is
doing great.
Alex is a technologist at NASA-JPL. He will tell us more about this later on. And Professor Vikki Meadows. How are you, Vikki?
I'm good, thanks. Glad to be here.
Thank you. Vikki is a professor at University of Washington, and she's also co-author of those two papers. So let's go straight to the topic here before losing momentum. So two papers were published, been accepted, in fact, and they're available on AstroPH at the moment. One of them is called Complications in the ALMA Detection of Phosphine at Venus. And Alex, you're the first author. So please, could you tell us a bit about what this paper is about?
Sure, yeah. We kind of divided this up into two papers because there were two main observations that were used to detect phosphine at Venus in the initial publication. And the first one was observations with JCMT, which Vikki and Andrew talk about more in their paper. And my paper talks about the observation with ALMA, which is the Atacama Large Millimeter Submillimeter Array in Chile. And so what I did for my paper, so when they initially published the results, I think it was back in September, their data from their ALMA observations is publicly available on the ALMA archive. Anyone can go in and download it and take a look for themselves. And so that's exactly what I did. I downloaded it, and they also provided the scripts that they used to reduce the data, which is kind of taking all the measurements and converting it into an image. And so I went through their procedures, and I pretty much followed their procedures exactly. There were some slight changes that I made on my end that really didn't have any kind of a noticeable impact. And I pretty much just ran through the data set and tried to recreate the spectra following sort of the figures that they had in their paper. And the result was more or less that I couldn't see what they saw. I couldn't see a line feature at the phosphine line, which is 1.12 millimeter, I think is where they're looking. So I wasn't able to identify the feature in the ALMA data. And something I also looked at in the paper was how the configuration of the ALMA antennas at the time, almost an interferometer, unlike a point in the telescope. It's made up of a bunch of different antennas scattered across a valley in Chile. And I looked at how that configuration might affect the spatial filtering of what you'll see, and how it might actually cause things that are more widespread at Venus, like SO2, to be not there and appear not there in the data. The reason that SO2 is so important in this context is because the line of phosphine that they detected in their paper is nearly co-located with another line that can be attributed to SO2. And so making sure that their observation wasn't contaminated was also something that they wanted to check out as well. So that half of my paper was saying, well, how could they not see SO2 given that it's everywhere in Venus, and kind of assessing why the technical reason for that based on the ALMA configuration. So that was my side of things, was all having to do with the ALMA part of it. And then, as Vikki will tell you, her and Andrew worked on the JCMT and the radiative transfer codes to actually investigate phosphine versus SO2.
Yeah, Vikki, so you co-author of this paper entitled Claim Detection of pH3 phosphine in the clouds of Venus is consistent with mesospheric SO2. So could you summarize the main findings of this paper?
Yeah, so Alex and our paper were very much coupled and actually feed back on each other. And so what we did is, when we heard about this discovery, it's obviously very exciting. So we're part of something called the Virtual Planetary Laboratory, and we have the modeling tools available to actually simulate what the spectra of Venus would look like for different abundances of different amounts of different chemicals in the atmosphere. So we thought, okay, fine, we'll do an independent assessment. We will use our model to see if we can fit the data that were published and see if we come to the same conclusion that it is phosphine. And so like a key part of what we did was we looked at, Alex just mentioned that the discovery line where they initially thought they had discovered phosphine also has an SO2 line there as well. So those two molecules absorb at the same space. So a big part of the argument for why this was phosphine and not SO2 in the original discovery paper was that they had not been able to see any SO2. And so they were able to put a limit on how much must be there. And so they said, well, if there's such a tiny amount of SO2 there, then clearly where this line has both phosphine and SO2, then it must be phosphine because we're not seeing any SO2. And so we went in to sort of model and have a look at whether SO2 would be a better explanation in this particular case. So what we did was we focused on the James Clerk Maxwell telescope data. Alex focused on the ALMA data, the Atacama Large Millimeter Array. And the interesting thing is, and this is quite a complicated story, but the interesting thing is the ALMA array was an array. And so it was an interferometer, and that's, as Alex showed, it was actually possible that even if lots of SO2 had been there, you would not have seen it. But we focused instead more on the JCMT, which is a single dish telescope. And so when it looks at Venus, it should see SO2 if it is there. Mm-hmm. And so what we did was we modeled the detection line on JCMT as if it was SO2. And so we learned a bunch of things by doing that. We learned that, in fact, SO2 at normal abundances in the Venus atmosphere would explain the data for JCMT. And we also discovered that the fit to that particular piece of data implied very, very strongly, we could prove it, that in fact, whatever was doing the absorbing was coming from well above the clouds. So this wasn't phosphine in the clouds coming from potentially a biosphere. This was something absorbing above the clouds. And SO2 fit that bill really well for a number of reasons. It fit the line, but it also was much more chemically likely to be up there. It turns out phosphine is quite fragile, and if it's well above the clouds, it would be destroyed very, very quickly. So we showed that, you would actually need a massive amount of phosphine coming from these clouds to be able to repopulate the atmosphere above the clouds to make sense. But SO2 is just there, and we know it's there. And so if you put in sort of the typical amounts that should be there, they fit the line just fine. The only problem with that is that, if we fit that JCMT line, then it would have predicted that there should have been quite a strong line in the ALMA data, the one they originally looked for SO2, should have been there, right, based on our simulations. But then Alex provided the missing piece of the puzzle, which was that actually no, based on the array structure, that would have been suppressed, you would not have seen it. And so our explanation of it being SO2, fits the line, fits the chemical arguments, and also would have predicted that there would have been nothing there in the ALMA data. And as the initial measurement was made, it had a very strong feature in the ALMA data, but on reanalysis, that feature became much weaker, and other people's reanalysis shows it's in fact gone away. So this is kind of science in action. People came up with a hypothesis, we came up with an alternative hypothesis, we made a prediction that actually there should be nothing in the ALMA data, and slowly over time, that's kind of where the community is going, that there doesn't appear to be anything significant in the ALMA data. So that's what we did. So our conclusion is that it's probably more likely to be SO2. That kind of hangs together.
So before I dig into some questions here, I would like to mention that we have people watching us from everywhere in the world. Thank you very much. Missouri, Reedville, Virginia, Oklahoma City, Istanbul, Italy, Cambridge in England, Connecticut, Canberra, Australia, Liverpool, Austin, Texas, Lecce, Italy, Seoul in Korea, Alaska, UK, UCLA. It's not a country, it's not a city, it's a university. Probably a colleague of us. Morelia, Mexico, New York, Vancouver, Canada, and Edinburgh in Scotland, and a lot of other places. Montreal, welcome, bienvenue, and the Philippines. So this is very interesting. The summaries that you gave, Vikki, is basically clarify most of my questions that I had about this paper. One thing I'm kind of curious to hear, it's why ALMA, which is kind of a new technology, a recent antenna, is not able to detect this, has not been able to detect this SO2 line. What is is it problem with the detector? Is it the fact that the way the structure of the array? And if there is a solution to this problem?
Yeah, I can answer that one. So the way that ALMA observes sources in the solar system or beyond, and how it's able to spatially resolve what's going on is highly dependent on how exactly the antennas are configured. So over the course of ALMA's operation during the year, it goes through several different configuration cycles. And generally, when you're proposing, you find a configuration cycle that's correct for the type of observation that you want to do. You generally know what resolution you need, what kind of what spatial resolution, and what's the largest thing that you can see accurately. Those are kind of the two parameters. And so ALMA has the main array, which is composed of 50-something 12-meter dishes that cover some of the longer separations between antennas, which lets you see finer features. But then it also has a compact array, which is 7-meter antennas that are spaced very close together. And so the closer together the antennas are spaced, the more accurate the larger scale structure of the image is in your result. And so what they did for this observation, the Jane Greaves and company, is they initially submitted a proposal for what's called director's discretionary time, which is, hey, we see something, we need to look at it now in the middle of the current cycle. We don't want to wait until the next cycle or something like that. And so when you submit that kind of a proposal, you are generally at the whim of whatever the antenna configuration is at the time. And so that is why their observing conditions were set up in a way that would have missed SO2 just because they didn't have enough antennas spaced close together. And instead the ALMA configuration was the shortest spaced antennas together were too far apart at that time. In the future, if you were going to make this kind of observation, you could include the Atacama compact array, which is the 7-meter antennas that are spaced really close together that I talked about earlier. And ALMA also has, like JCMT, a single dish observation feature. So you could make a JCMT-like observation with ALMA as well. It was just, I think, a matter of scheduling. They thought it was important to get the data very quickly and just to confirm the results they had seen with JCMT. So,
all right. I have a question for you, Vikki. So in your paper, you mentioned about the SO2. So first of all, just briefly, what could be the source of SO2 on Venus, so people understand?
Okay, so sulfur dioxide, SO2, is actually the third most common gas in the Venus atmosphere. So after the dominant, massive carbon dioxide plus nitrogen atmosphere, that is the bulk of the Venus atmosphere, SO2 is the third most abundant gas. And so it could have a volcanic source. It could be sourced from the clouds, which are H2SO4. So, having a lot of S plus O floating around is certainly not an uncommon thing for Venus to have, partly because of that big reservoir of H2SO4 aerosol from the clouds. And also the fact that, there may still be tiny amounts of active volcanism still going on Venus. And so you may also get SO2 being outgassed as well. So it's a very common gas in the Venus atmosphere.
And it's not a biological signature. We have geological way of forming SO2.
Right. Yeah, not in this context. I mean, I really do want to make that point too, that when we go out looking for signs of life, that it's sometimes very difficult to interpret something without looking at the context of the environment that you find it in. There may be some instances where SO2 might be more indicative of life, but in that environment, in the Venus environment, it's much more likely to be produced by things that aren't life. And so it's really important when you look for life to also look for the environmental context of what you're finding your interesting signal in.
So one of the key findings in this paper is that the location of the source, the mesosphere, 80 kilometers above the surface. And you mentioned in the paper that if this was coming from phosphine, considering, as you mentioned, the fragility of the phosphine molecule, it will mean that the production of phosphine will be 100 times larger, higher than the the production rate of photosynthetically generated oxygen on Earth. Can you explain this in normal languages so people understand?
Yeah, so basically, you know, how much of a given gas is in the atmosphere will be a product of how quickly it gets delivered to the atmosphere versus how quickly it gets destroyed. And for phosphine above the clouds, it's exposed to the ultraviolet radiation that's coming from our star. And so it is very susceptible to being broken apart by UV radiation. And also there are reactions because this is a very oxidizing atmosphere. It has a lot of oxygen in it, a lot of CO2, a lot of O in there. Phosphine, being a molecule with a lot of H in it, will tend to be destroyed by reactions that are going on there. So but the photolysis, and there's also actual reactions occurring amongst, because that phosphine is reactive with that type of atmosphere. And so because of those aspects, it gets destroyed very quickly. It has potentially a sub-second lifetime. You know, a little phosphine molecule comes above the clouds and goes, ooh, that's the star. I wonder if it'll be friends with me. And then zap, you know. So it basically has a very, very short lifetime up there, which means for us to see potentially the 20 parts per billion that people thought they were seeing, you would have to keep supplying it. If it goes up there and goes zap within a second, you have to keep supplying huge amounts of phosphine to get it to be in the atmosphere. And so, you know, we did a quick calculation and showed that actually the rate at which you'd have to supply phosphine to that upper atmosphere, because that's where the absorption was coming from, would be something like potentially 100 times the flux of oxygen off our, you know, oxygenic biosphere, our photosynthetic biosphere. So that makes the phosphine chemically unlikely. We would say that is unlikely that amount of flux would be present, would be happening. So, and flux is just the rate at which something is delivered to the atmosphere.
Thank you. Thank you for this explanation. So I remind our viewers that we're going to take a few questions. So if you have some, please feel free to post them on the chat if you're watching us on YouTube, Facebook, or any other social media like Twitch. I have a question for both of you here. So you're not the only ones making this, refuting this, the existence of phosphine in the atmosphere of Venus. Could you tell us why there is so many papers on this? I noticed that you list them in your paper. There is Ancronas et al., Snellen, Villanueva, and there is probably more of them. Could you tell us first why so many? Are those papers similar to yours? Are they doing something very different? Did they all reach the same conclusion? And then I have a kind of a non-scientific question: is why there is so many papers refuting the existence of Venus, phosphine on Venus? Alex, you want to start?
Yeah, I'll let Vikki answer, because there's two sides to this question. There's I guess the scientific side and there's the technical side. The reason that there were so many, and I'll talk specifically about the papers that were talking about their observations. And those are the ones by Ignace Stellen's group, the one by Geronimo Villanueva's group, and then there was the response by Jane Greaves as well. So initially, Jane Greaves and folks put out their initial paper, which was their ALMA data that they had taken, and their JCMT observations as well. Those are all publicly available in the archive. And so we both started looking at it, but some other groups started looking at it as well. And I think the first two papers were by the Villanueva and the Snellen papers. And what they were doing is they were trying to essentially re-reduce the initial ALMA data and see if they could recreate the feature similar to the way I was doing it. But something became apparent pretty quickly, and that was that the initial ALMA data had some calibration issues. And so that was determined by the folks who were working on that there was a problem with how the observatory was recommending that the data be calibrated. And so then the data got kind of taken back into what they call QA3, which is just a quality assessment phase. And so the observatory staff started working with the original authors on the calibration issues, and then they released kind of a next update. And so then after that point, after the two initial papers had been published focusing on the initial incorrect calibration, Greaves et al. Put out a response to their paper that was their interpretation of the revised calibration with ALMA. And then what I did and what we did is we looked at that revised calibration procedure that the observatory put out, and then we ran that through, and we still couldn't see anything agreeing kind of with the original assessment by the Snellen and Villanueva groups. So it's kind of just that part of it, why there were so many papers from the technical side, is because there was that big issue that was found in the ALMA data that was found after all of the other groups had written up their interpretation of the results. And so we said, hey, we need to take a look at what the observatory is recommending as kind of the final product here. So I'll let Vikki talk to the scientific side of why there's so many papers.
So there was the analysis of the different data sets, essentially if they came out with different calibration. But yeah, I think what you're seeing here is the scientific method in action. So, we don't often see this as scientists, things come out and people don't necessarily challenge them. But this was such an important and significant result that I think a lot of groups around the world brought to bear what they could contribute to the science of this. So, science isn't just putting out something and everybody believes it. It's putting out something and having people try to see if they can verify it or disprove it or, support it in some way or otherwise. And so what we saw here was sort of multiple lines of investigation that came out of this. And Alex talked about one of them, which was, okay, the first point when looking for a biosignature is like, okay, have I actually detected something, right? So what Alex described was a group of researchers who had expertise with that type of telescope, who said, okay, I'm going to try and help, strengthen your case or show that I have an alternative, conclusion on the have we actually detected something. So they went down that line to see whether or not they could verify the initial detection. My group was looking at, okay, have we interpreted this correctly? If something really is there, do we have the right explanation for what we think we're seeing? And so there was a group of people who went down that line. The Villanueva group, as well as our group, also looked at the potential of it being sulfur dioxide rather than phosphine. So we looked at that. And then there was a third group of people who took another tack, which was very important, which was saying, okay, if we think this is phosphine in a blended line with SO2, which is tricky to interpret. Let's see if we can strengthen the case by going and finding evidence of phosphine at other wavelengths with other telescopes and other instruments, not in the same observing mode, but different independent measurement techniques. Can we see phosphine at other positions? And so there was another slew of papers that came out and said, okay, the Akins one, for example, they went and looked at existing data that had been taken by ground-based telescopes that should have had phosphine in the wavelength range they were looking at. So they were sensitive to a certain part of the spectrum. So they went looking for phosphine, they did not find it. And so they were able to put what we call an upper limit, basically on how much could have been there. And then another team used spacecraft data from Venus Express, the SOIR, I guess, instrument, which was looking at near-infrared wavelengths where there could potentially have been phosphine lines. They also had the sensitivity to potentially see it if it was there. They did not. They were able to put an even more stringent limit on how much phosphine could be there. So this was science in action. This was all of us, verifying the observations, looking at the interpretation, and then trying to find corroborating data at other wavelengths that would strengthen the hypothesis. So that's what was happening. The community was responding.
Yeah, this is important for viewers to understand that, yeah, science evolves. Science is not like we don't write something on a book and then we say this is the truth. There is always a scientific conversation, and ideas that we take for granted sometimes are challenging 10, 15 years later. But in this case, the idea popped up in September 2020. And since then, multiple groups work over the past 6 months, refining the observation, understanding the observation, finding other hypotheses, other explanation. And right now, obviously, there is still a large group of people who believe that there is no clear detection of phosphine from these two sets of data. Is that a good summary?
Yeah, I think I would say, as a scientist, I would say it is unlikely that is the interpretation, but I can't absolutely disprove that it is not there. That is difficult to do. But I'll throw this back to Alex to say that I think what we need to do as scientists is, again, we have two competing hypotheses. We now need to take some data that will discriminate between those two hypotheses. And so, I don't know, I'm taking over your interview, Frank, but maybe Alex can talk a little bit about
that was a good position.
What we need to do next to try and distinguish between these two hypotheses.
Yeah, and so like Vikki said, you could continue observations at other wavelengths that would be able to detect phosphine, but even going back and making new observations with ALMA. I think they can't make the same observations with JCMT right now that may be able to in the future. It's just a receiver issue. But you could go back and structure an ALMA observation that was a little bit more able to clear up some of these questions, whether you choose different spectral resolutions, different antenna configurations. There's a way to go back and look at this again that will be able to paint a much clearer picture. So yeah, I think now that the doors are open on this, it's definitely worth figuring out, because if phosphine is there, it will be very difficult to detect based on our understanding of Venus's atmosphere. And, you know, if there is there, it's some there, it probably isn't much. And so we need a really sensitive measurement, whether from the ground or from space, to really make that distinction. But we can't say for certain that it's not there.
Yeah.
So we have questions on this topic, so that's why I want to interrupting you. You work at NASA-JPL as a technologist. So first, you're going to tell us what is a technologist, and two, a lot of people asking is, are we going to send a space mission on Venus, something that float in the atmosphere to capture some samples and analyze that? Is there a mission like this planned? Or another one, and the type of technology that will help us knowing the composition of Venus atmosphere, at least?
Yeah, so there's two missions that are being considered by NASA right now. The first is Veritas, the second is Da Vinci. These are two small class missions. I don't believe that either of them were, when they were initially formulated, had any idea of going to look for phosphine. I think the Veritas is a radar mission, and Da Vinci is an atmospheric probe that will be measuring the atmospheric composition. However, I'm not sure if they've made modifications to those missions now in light of this discovery, but there are missions that are going to are competing currently with other missions to go to Venus. And I think there are 4 small missions that NASA is considering, and 2 of them right now, the Veritas and Da Vinci, are Venus. So with any luck, one of those will be selected. And there have been folks in the community who have been working for a while now on next generation mission concepts, like a floating platform in the clouds, a long-lived aerial platform, planes, all kinds of different wild concepts for exploring Venus. So I think that there's been a lot of work on how to do that. And it's just a matter of proposing those missions and getting NASA to see that they're a worthwhile investment.
So that's your role as a technologist to do this?
Oh, no, yes. So as a technologist, and it means different things at different organizations, but at JPL specifically, we're kind of half scientist, half engineer. We're the folks who have knowledge of certain kind of classes of instruments. For me, my background is microwave remote sensing, millimeter wavelength remote sensing. So most of my work is figuring out, it's ranging everything from the design of those instruments to how can they be used scientifically to get interesting results, modeling, simulation, all that kind of stuff. So I kind of sit between the scientists and the engineers in the range of activities at JPL.
Thank you. So we have a question. I think, Vikki, you're gonna want to take this one. Despite the I'm repeating the question. Despite the inaccuracy of this study, what you have done so far, your group and others, may have increased the scientific focus of the study of Venus. So maybe you learned something new about Venus from this. Can you tell us?
Oh yeah, absolutely. I mean, and I'm a Venus scientist. I did my PhD on Venus, so I really love Venus. Even though I work mostly on exoplanets now, I'm definitely a Venus scientist from way back, which is also part of why we kind of leapt up. So I'm both an astrobiologist and a Venus scientist. So I was like, okay, this is something I really want to work on. And I had teams and students and people who were trained. We didn't have the ALMA expertise, which is why we started the collaboration with Alex, which was very productive. Essentially, I just want to say that Venus is intrinsically fascinating, even if we don't find phosphine there. And I think also Venus is a really great astrobiological target, but people don't realize this. And I think you don't need to find life in the clouds of Venus for it to be astrobiology relevant. In particular, it's sort of an example of an alternative history for Earth that is a terrestrial planet that has lost its habitability, possibly had an ocean. It's lost its ocean over time, and we see a signature of that in the atmosphere. it's a truly fascinating place if you want to try and understand habitability and how planets lose that habitability. You can think of Venus also as kind of the end state evolution for a terrestrial planet. It could be that there are lots of Venuses out there in the universe and in the nearby, local solar neighborhood. And some of the very first exoplanets that are small enough to be rocky, the terrestrial exoplanets, some of the very first ones we will study will probably be Venus analogs because they're closer to their star and they're more observable to us with our telescopes using the particular techniques we use. So Venus is a fascinating example of the end state of terrestrial planet evolution, a likely prototype for things that we're going to be studying out there really soon, and just has a lot of fascinating processes that we still don't understand. It's like you would call it the girl next door. It's only 0.3 AU away at closest approach, and yet we still don't understand things like the motion of the clouds and the propagation of gravity waves. The chemistry, it's showing us that we really don't understand the chemistry. If it turns out that traces of phosphine are in fact there, then we're gonna have to rewrite all of our chemistry of Venus, right? So this has been, yes, a very interesting discovery for kind of raising the profile of what I have already considered to be a fascinating planet.
Hi, Alex, you want to add something about the future of Venus? Is it dead?
Yeah, I think Vikki explained it pretty well. I mean, there's been, I think even before this observation, there's been growing community support for us to send something back to Venus. The success of the Venus Express mission, the success of the Japanese Akatsuki mission, I think that we're really there's a lot of different reasons to go there, whether you're looking at the atmosphere or the surface, and so I think that to the extent that this has kind of helped remind everyone why Venus is so important and why we still don't know so much about it, I welcome it in that sense. We still have a lot more to do.
All right. Well, thank you very much to both of you. I just want to make a correction here. Vikki reminded me that those papers are accepted and published as in APJ letters, so you can read them, have a look. You see they are fascinating. They're fun to read. Read it the way we read scientific paper: abstract, conclusion, look at the figure, and then you see if you want to read the details. But thank you very much to both of you for your time, for telling us about this interesting work you're doing on the search for life on Venus. I mean, even if there is no life on Venus, we learn a lot, and that's the main point here. If our viewers want to learn more about a place where we can find life called Mars, we have a SETI talk, March 24. We invited researchers who are involved in the Perseverance rover, and they are going to tell us how we can find life on the surface of Mars. So check out the registration link, which is in the comments. And thank you for watching. Don't forget, we are a non-profit organization, so we are depending on your donations. So if you feel generous today and you like what you watch, what you heard, what you're seeing, make us a donation. Visit our website at seti.org. We appreciate also, we just say some positive comments and Tamak, or join simply our YouTube page and get notification when we have a new SETI Live, SETI Talk, or Science Bites. Sign up for our SETI Talks events. Join us. See you on March 24 to talk about the Perseverance rover. And Alex, Vikki, thank you very much again. And I hope to see you soon to talk about another place, another planet, or maybe an exoplanet.